Hey girls, I am inside the chicken coop today, and there's all three girls, Lucy, Nancy, and Daisy. And in this video, they're gonna do a team effort at explaining some carboxylic acid functional groups to us.
All right, girls, so in this video, we're going to talk about carboxylic acids. And carboxylic acids are actually quite an important class of organic compounds because just like alcohols, they're everywhere in nature. They're even in your most of your food and definitely somewhere in your kitchen. Um, Carboxylic acids are characterized by a carboxyl functional group. And in semi-structural formula, we write it as a COOH in the molecule. In full structure, that's what it looks like right there. And I touched upon this in the last video where we oxidized alcohols into carboxylic acid. So we can very easily turn alcohols into carboxylic acids just by reacting it with oxygen in an oxidation reaction. And this this functional group is probably the biggest functional group you would have to deal with this year. And this functional group involves the carbon double bonded to an oxygen and then single bonded to a hydroxyl group. So that if you're asked to ever circle the carboxyl functional group, you circle everything, that carbon, the two oxygens, and the one hydrogen. So carboxylic acids are weak acids, and they are often found in food to give it a sour taste. So the vinegar that you find in your kitchen usually contains about 5 to 20% ethanoic acid, which is this structure right here. It's also used as a form of defense in nature. So ants use methanoic acid or formic acid. They store that somewhere in their body and they spray it whenever they sense danger, and that wards off a lot of their predators. So let's talk properties. So just like hydroxyl groups, that OH portion of the molecule, as well now as the carbon double bonded oxygen part of the molecule, can form hydrogen bonds. And look at the picture on the left, you can see that two carboxyl groups have come together in an interlocking hydrogen bonding formation, and we'll talk a bit about that in a second. But the oxygens in the carboxyl group have partial negative charges. The hydrogen has a partial positive charge, and that's shown by the delta negatives and the delta positives in the molecule. So these positive and negative line up fairly well. And in fact, they line up so well that, have a look at the diagram on the left again. The two molecules of carboxylic acids can come together and form a dimer. A dimer is when two identical molecules become bonded together. In this case, they are hydrogen bonded together. So that's a H bond. And so is that. And that essentially gives the molecule quite a strong intermolecular forces. And this gives carboxylic acids high boiling point, higher than alcohol, and we'll have a look at the graphs of that later. But hydrogen bonding between the carboxyl group and water can also occur, just like the diagram on the right, and this gives carboxylic acids high solubility in water because they can also hydrogen bond to water, and just like alcohol, the solubility of carboxylic acids decrease as the length of the hydrocarbon chain increases. So if we if we, for example, add more carbons through here, the solubility will decrease because all of this part is non-polar. The only polar part of the molecule is the carboxyl functional group. So that's the polar bit, and this is the non-polar bit, and it's a bit of a compromise. As the non-polar bit gets longer, solubility in water decreases. Okay, so let's keep in mind of the dimer formation that we talked about before, how two molecules of carboxylic acids can come together and form this dimeric structure via two hydrogen bonds. And this gives carboxylic acids a higher boiling point than alcohols that can only form one hydrogen bond. And when comparing two molecules of similar size, one containing a carboxylic acid functional group and the other containing a hydroxyl functional group, the carboxylic acid functional group containing molecule is going to have a slightly higher boiling point. And the reason for that is to do with the dimer formation. Okay, and here we come to the nomenclature part of the slides, and here we're going to talk about naming carboxylic acid molecules. All the previous rules of naming still apply, and the names of carboxylic acids end in oic acid. So ends in oic acid. For example, ethanoic acid. Ethane tells me that there's 2 carbons, and oic acid tells me that it's a carboxylic acid. And that means I can now draw the molecule as, so it's got 2 carbons in total, and it's got a carboxylic acid functional group, and that's what it would look like. 2 carbons, 1, 2, and that's the whole molecule. Now, here is the key point. The carbon in the carboxyl group, so this carbon there, or that carbon right there, must be included in the parent chain. So it doesn't matter if it's a shorter chain, it must be included in the carbon chain. And the carboxyl carbon, so that carbon right there, must be numbered 1. So you don't get a choice of which end you number from. If it's a carboxylic acid, then the carbon of the carboxyl group is always 1. So when numbering this molecule at the top, it's going to be 1, 2, 3, 4, 5, 6. Okay, let's give it a name. It's 6 carbons, so it's it's hexanoic acid, 2 words, hexanoic acid. And we have a branch. There's that branch. It's a methyl group of carbon number 5. So it's a 5-methyl hexanoic acid. So the naming of the branching is quite generic. The skills there apply to all different functional groups. You just got to be able to identify the longest chain with the functional group in it, be able to number it the correct way, and then the naming should fall in place, including the branching. All right, so let's have a go at this one. Again, same drill. Let's pause the video. You have a go, and then unpause and watch me as I model this for you. All right, so hopefully you've had a go, and now let's apply some of these rules to naming this molecule. So I always identify the longest carbon chain. That's always the first step in naming. So there it is right there. And it's 5 carbons long. So I'm going to write pent. I can see that there's a carboxyl group, and I'm just going to circle the entire carboxyl group in green. There it is right there. So that carbon has to be carbon number 1, 2, 3, 4, 5. So it's a pentane oic acid. So that's how we finish. That's the parent chain done. It's a pentanoic acid. It's got a branch here that is coming off carbon 3, and it's a methyl. Another methyl branch coming off carbon 4. So we write 3, 4 dimethyl pentanoic acid. And there's the name completed. 3,4 dimethyl pentanoic acid.